This video introduces the deployment of accuracy drift autocorrection in the eye-to-hand vision system. Here, we use the example of picking neatly arranged housings. By deploying accuracy drift autocorrection in eye-to-hand vision system, you can avoid decreased picking accuracy due to temperature changes. Additionally, by setting a correction cycle, you can achieve long-term picking stability. Before deployment, make sure that the workstation has a solution for picking. Confirm that the accuracy of the camera, robot, and extrinsic parameters have been checked, and ensure the robot can accurately pick the target objects. Make sure there's enough space for mounting the calibration sphere. Now, we can start the deployment. Here are all the steps for deploying accuracy drift autocorrection in eye-to-hand vision system. Let's begin with the preparation. First, check the items for deployment. Open the eye-to-hand kit packaging box and take out the items, including a calibration sphere, a soft nozzle air blower, and others. Start by mounting the calibration sphere. In eye-to-hand setup, the calibration sphere should be fixed to the end of the robot's arm, such as on a sturdy gripper or on the flange plate. Make sure that the calibration sphere can reach all the areas where the target objects will be picked, and that it remains in the camera's field of view when moved. In scenarios where the robot needs a large or long gripper for picking, avoid any collisions between the gripper or calibration sphere and surrounding objects. Next, warm up the camera to prevent changes to the intrinsic parameters due to temperature fluctuations during data collection. Then, set the parameter group in Mech-Eye Viewer to ensure that the point cloud of the calibration sphere remains smooth and intact. Now that the preparation is complete, let's move on to deploy the drift autocorrection tool in the software. Open Mech-Vision. Navigate to Toolkit. Click Error Analysis Tool, and then Autocorrect Accuracy Drift in Vision System. Select Autocorrect Accuracy Drift in Eye-to-Hand Vision System. The 4 steps for tool deployment are displayed in the deployment wizard. Click Start and begin collecting workstation data. Enter the workstation data to calculate the number and distribution of the image capturing points where the calibration sphere images are captured. Connect to a camera. Select the project for picking. Select the corresponding calibration parameter group. Choose the parameter group configured earlier in Mech-Eye Viewer. Next, set reference object. In this video, we use a 60 mm diameter calibration sphere for demonstration. Then, set the scenario of the scene. In this video, housings are neatly arranged in one layer. Thus, choose one for the object layout. Move the calibration sphere to the position of the bottommost workpieces. If there is a risk of collision between the gripper and objects below, you will need to set the distance from lowest sphere to lowest object. Please fill in this data based on the actual situation. Next, fill in the space dimensions of target point cloud, which refer to the dimensions of the point cloud model of the target object within the workspace. Enter the length and width of the working space according to actual situation. In this scenario, since the housings are arranged in a single layer, the height of the target point cloud is equal to the height of the housing's point cloud in one layer. For housings, the point cloud model is created using multiple layers of the surface point clouds. The height of the housing's point cloud is the distance between its upper and lower surfaces. Therefore, the height of the workspace here is the actual distance from the upper surface to the lower surface of the housing. Once completed, click Start Calculation to compute the number and distribution of the image capturing points for the calibration sphere. Next, validate image capturing points. Calculate the repeatability of the poses of the calibration sphere from each image capturing point, so as to ensure accurate and reliable data for accuracy drift correction. In this step, you can see the calculation results, and also the number and positions of the image capturing points. Based on these results, you can determine the positional relationship among image capturing points. According to the illustration, move the robot to 9 validation positions in sequence. After reaching validation point 1, record the robot flange pose in the software. At this point, adjust the ROI of the sphere to ensure that the sphere can be repeatedly and accurately recognized. The ROI must fully enclose the calibration sphere, leaving a margin equal to the sphere's diameter on all sides. Once done, click Capture Image to validate. In the pop-up Validation Success window, you can view the 2D image and 3D point cloud of the calibration sphere. Click OK to proceed with validating the remaining points. Move the robot to the remaining image capturing poses, and record the poses for validation. Afterwards, click Next to enter the interface of generating example program. The result of the validation points are displayed here in the list. Based on the results, a robot example program will be generated by the Drift Autocorrection tool. You can select the robot brand in use and export the example program, which will assist in the subsequent drift autocorrection. In this video, we use a KUKA robot as an example. If your robot is not in the list, you may skip this step and write the robot program manually. Finally, enable autocorrection to correct the accuracy drift during actual production. Navigate to the project interface. 2 new projects appear in the list. The first project is used for collecting the calibration sphere's data, and the second one is for generating the system drift autocorrection model. To ensure that the picking solution can correct accuracy drift with the autocorrection model, it's necessary to select Autocorrect Accuracy Drift in Vision System in the Output step. Next, load the example program to the robot system. After loading the program, teach home position manually. In this position, ensure that the robot does not block the camera's field of view and that no collisions occur when the robot moves to the first image capturing point. Then, confirm that the IP address and the port number in the XML file for this command match those used in real-case scenario. Next, run the drift correction program to test whether the robot triggers the project to generate calibration spheres poses and the drift correction model. Return to the tool interface. In the Data Monitoring dashboard, a record of system drift autocorrection is generated. Here, delta X represents the drift compensation for the X value of the calibration sphere pose. The same applies to delta Y and delta Z. Finally, verify the effectiveness of the deployed drift autocorrection solution by performing a test picking. Run the picking program. If the robot can accurately pick the workpiece, the deployment of the system drift autocorrection in eye-to-hand vision system is proved successful. To ensure long-term stability of the actual production, configure the drift alert threshold here after testing picking. Normally, the threshold is suggested to be set at 10 mm. If the actual drift exceeds this value, check the stability of the camera, the tool, and whether the robot's 0 point has been lost. These are all the steps for the deployment of system drift autocorrection in eye-to-hand vision system. The autocorrection cycle can be set based on the site situation. It is recommended to perform drift correction at least once a day before production. You can refer to our documentation for more information on eye-to-hand vision system drift autocorrection and calibration sphere maintenance. For more information on flexible maintenance after the deployment, please watch our video, Vision System Accuracy Drift Autocorrection, Quick Camera Replacement.